So my name is Alex. I work with Costas and Ken and several other people in this room, particularly on kind of algorithms for event-based cameras at the University of Pennsylvania. So today I'm going to talk about some of the work that we've been doing on kind of learning for event cameras, particular unsupervised learning methods. So I probably won't need to go through this too much. You're going to hear this to death today. But some of the motivation for why exactly we might want to use event cameras is, one, things like dynamic range and also kind of high-speed motions, which traditional cameras might run into problems with in kind of these kinds of edge cases. So as a high-level overview of how the camera actually works, basically you can model the intensity at each pixel as kind of this continuous value. And whenever the intensity changes over, or the log intensity changes over a given threshold, which is theta here, the camera will basically tell you that an event has occurred. And this event encodes the XY position of this change, a timestamp here, which is typically accurate down to microsecond levels. And then it gives you a polarity, which is basically whether the intensity got brighter or darker. It's a binary value. So at the bottom, we have kind of a visualization of the kind of events you would expect on a fast-moving object. So this is just a spinner that's just going around in circles. And in the back, you have the grayscale image, which is kind of just this white circle. It's moving so quickly that the image is just completely blurred out. On the other hand, we have the events here in red and blue, which are positive and negative events. When we represent them in 2D, you can still see that we have some kind of motion blur here, right? The lines are a little thicker than just the edges of the spinner. However, if you look at this in kind of a full 3D representation, where we have Y in the image going up, X going into the screen, and time going across, you can see that we actually retain all of the motion information inside this scene. You don't run into things like aliasing or motion blur. So these cameras basically allow us to basically track potentially very, very fast motions without the need to have very, very high frame rates. So like I've kind of alluded to, three main benefits of these cameras are, one, low latency and the ability to track these fast motions. And they also have very, very good high dynamic range. So like in the video or photo that you saw from Davide before, if you point this camera at the sun and then wave something in front of it, you're going to see both things just fine. And also they have very, very good power consumption. However, I think one thing that's not immediately clear is that the latency and the dynamic range here are not actually independent from each other. They're coupled for traditional cameras. And that's because when your scene gets darker, typically what you need to do is increase your exposure time. And as you increase your exposure time, then you start blurring for much slower motions. So it's not like these cameras are only good for kind of this one class of very, very fast motions. In fact, they're actually good in kind of this area between this green and this orange curve, where as it gets darker, they start getting better for even kind of relatively slow motions. So our group at Penn comes from a relatively traditional computer vision and robotics background. So we first started off in this event camera space by basically just trying to design algorithms that resemble things that we know and know work well in the traditional computer vision literature. So one of the first things that we did was feature tracking for events. So here I basically took the camera outside and just waved it around as quickly as I could. And here we have basically a feature tracking algorithm that uses an expectation maximization to basically solve for optical flow for a small window of events. So if you concatenate this over time, what you get is basically pretty reasonable feature tracks over long periods of time. And once this works, you basically get these benefits of the camera for free. This kind of high dynamic range and low latency. These come very nicely just from the camera itself. Once we had this, we fused this feature tracking with an IMU. And this allowed us to get accurate estimates of the fixed-off camera pose. So here we have a monocular event camera mounted downwards on a quad rotor, and we kind of flew over this concrete surface outside our lab. And from the events and the IMU alone, we're able to get very good camera trajectory estimates over a pretty long trajectory. So every one of these white squares here is about a meter. Finally, we've also worked on stereo depth estimation. So given two event cameras mounted horizontally next to each other, how do you estimate the depth of every pixel in the scene? So in this work, we leverage the assumption that we know the camera motion. And if you do this, it turns out that you can use this kind of event focusing technique to improve your depth estimates. So now we're able to get very accurate depth estimates from a stereo pair of event cameras as well. Of course, it was great to have these really good results, but one problem is developing algorithms is just really, really hard. You need a team of PhD students, you need months to work on these kinds of things, and in particular for events, we ran into a few main problems. One is that we need a substitute for the photometric loss. So for traditional images, you can tell whether kind of 2 points come from the same point in the world by looking at their intensities and seeing if they are similar. Do these things actually look alike? But with events, you really only get change information. And so it was unclear for quite a long time how to kind of replace this photometric loss with something that also works for events. So these days, I think this focusing technique works very well and can almost be dropped in for most kind of motion type tasks. However, other problems are things like needing some kind of model for event noise, not only in the timestamps, but also in kind of noise and events that come up when they shouldn't, and things like that. And then even if you kind of model everything correctly and you have a good loss function, you still have to solve a relatively complex optimization problem. And if it's a nonlinear problem, you would need to find some way to initialize it properly so that it converges correctly. So this is kind of where we see deep learning coming in as a possible solution for at least some of these problems that we run into. So as we've seen in CVPR over the last 5 years to a decade, neural networks allow us to solve really, really complex nonlinear problems in a manner that's a lot easier than kind of traditional optimization. They can also pretty good at learning kind of underlying noise models implicitly if you give it the right loss function at training. However, for event cameras, the issue here is that it's relatively hard to get data. These cameras really aren't that old. They've only been around for a few years. And so you just don't have things like ImageNet for events. So we don't want to have to rely on kind of hand labeling data ourselves in order to train our networks. And so that's where we kind of got into this concept of self-supervised or unsupervised learning, where we can train neural networks with losses that are basically based on geometry, instead of having to actually label every single output that we want from the network. So we started this by generating a data set. So if you want to do deep learning, regardless if it's supervised or unsupervised, you need data. So I think in ICRA of last year, we generated the multi-vehicle stereo event camera data set, or MVSEC. The name is pretty descriptive. Basically, we have a stereo event camera, which we mounted below a Velodyne LiDAR, which gives us basically very, very accurate depths. And then we also attached a stereo traditional frame-based camera for reference. And then we also have things like GPS and motion capture for ground truthing when available. So we took this rig and we stuck it on whatever we could find. So here it's on top of a car, we have a hexcopter, we have a motorcycle, whatever you'd like. So in this data set, we provide ground truth poses and depths, which we collect from various sources such as motion capture, odometry, things like that. So this is a preview of kind of some of the sequences that are available. If you're interested in the data set, we have the QR code and the link here. And we actually have the files now available in an HDF5 format, which you can read in basically any language. So this is basically the kind of ground truth that you can expect from the data set. This is a map generated from our lab, which is just a local map from LiDAR, odometry, and mapping. So for small scenes like this, we're able to get very, very accurate pose and depths just from a standard odometry package. On your right, we have a relatively longer sequence. So this is 4 kilometers of driving outdoors. And here we leverage Google Cartographer with loop closure to enable us to still have very, very accurate poses, even for very, very long trajectories. So this data set basically allowed us to have access to high quality data so that every time we want to develop something new, we didn't have to go out and collect it ourselves. So this is what some of the other data looks like. This is the outdoor driving sequence that we have. So this is driving through West Philly. I think this is the 4 kilometer sequence. And on the left, we have the events coming from the camera. We also provide the grayscale image. And here we have the ground truth depths with the camera posed visualized in green over here. So we have many of these sequences, and we found that these have been very useful for training things like CNNs, for kind of these geometric problems at least. So once we had all of this data, we approached this kind of training problem from an unsupervised perspective. So we have works from RSS last year, and also we're presenting a work here at CVPR for estimating things like optical flow, and motion and depth directly from events without any kind of direct supervision. So the main contributions of this work were kind of these frameworks to do self and unsupervised learning, where you take in only events and then you predict some kind of geometric output. The main challenges here are, one is actually, how do you actually represent these events for a CNN, right? They come in as, you can think of them as kind of this n by 4 matrix, or a constant stream of 4 by 1 vectors, which is just x, y, time, and polarity. But for traditional CNNs, they kind of expect things that look like images, right? They exploit the kind of the spatial locality inside your image, and it's hard to do that if your input is just a n by 4 matrix, for example. So I'll talk about how we resolve this problem. And then we provide supervision from the network, either from the grayscale frames that also come from the Davis camera, or more recently we use kind of this motion blur or kind of focus loss that Guillermo talked about earlier. So as a preview of what to expect, this is kind of the output from our network. It takes as input directly the events from the spinning fidget spinner, and for every single pixel with an event, it'll give you an optical flow. So you can see that once it's trained, you get all the benefits of the camera essentially for free. So it works for very fast motions. It'll work for a large number of different lighting environments and things like that. So as a little background into kind of unsupervised and self-supervised learning, this is one of the first works that did this for kind of the full geometric ego motion and depth problem. And at least for images, the idea here is that you pass into the network a pair or maybe a triplet of images, and the network will give you some estimate of the motion inside the scene. So in this case, the network will tell you the depth of every point and also the relative pose of the camera between these pairs of images. So from these estimates, you can estimate, for example, this point in the image, where it would have come from in the previous image and where it will move to in the next image. If this estimate is correct, then the intensity values at these pixels should line up. They should look pretty much the same. And if it's wrong, then hopefully it'll project you to somewhere else, which will give you basically a higher loss value. So if you do this for every single pixel in your image and you just backpropagate through your network, it allows your network to basically learn, in this case, the depth and ego motion completely unsupervised without any labels or anything like that. So we do something very similar in our work. But before I get into that, I'm going to talk about some of the kind of input representations that we've tried for these kinds of events. So in our work in RSS last year, we first started with this idea that, well, if we want to estimate optical flow, really the most important thing is the last timestamp at each pixel. As long as you don't have a really dense scene, if you look at this is an image of the last timestamps, you can see that the timestamps kind of encode the direction of the motion inside the scene. So as an input, we encoded the last positive and negative timestamp at each pixel. And then we also gave the network the number of events at each pixel. And this kind of allowed the network to filter out things like noise, where you just have a random event popping up every now and then. However, one problem that you'll find with this input representation is that if you have a really dense structure like this board over here, then the newer timestamps will tend to override the older ones. And you might end up with just kind of this mess, which is just all very recent timestamps, which doesn't give you very much information. So what we've kind of settled on now is this kind of volumetric representation of the events, where we take a subset of the events, some number currently around 15,000, and then we discretize the x, y, and t dimensions. So it's a volume in x, y, t. However, instead of just rounding the events and sticking them into this volume, which may kind of lose a lot of this temporal resolution, we insert events into this volume using something that's similar to kind of trilinear interpolation. So the closer an event is to a certain bin, the more you'll actually increment that bin's value. And this allows us to basically retain some of the high temporal resolution that we have from the events. So we take either of these input representations, and we pass it through what's a relatively standard CNN. So this is an encoder-decoder network where you take your input, you pass it through a bunch of convolutions where the spatial size decreases, but you increase the number of channels. So this kind of compresses the information into a lower dimensional embedding. And then we have a decoder, which then blows it back up into the full resolution of whatever output you desire. We also potentially have a secondary pose network, which will then give us the relative pose between the start and the end of the event volume, essentially, since you don't have actually frames in this case. So for something like this, it's a relatively small network. It'll run on something like my laptop at around 20 hertz. And if you have a lot of money to spare, if you have a V100, for example, it'll run at about 75 hertz. So now I'll talk about kind of types of supervision that we've tried for these networks. The first thing we tried was basically to use the grayscale images that come concurrently with the events. So the idea here is that you take your input representation for the events, feed it through your network, and you'll get some estimate of optical flow coming out. So at the same time, you'll also have the grayscale images for the start and the end of your event volume. So you can take this optical flow that comes from your network and just apply the same photometric loss that you would as if you had images coming in. Because the camera gives you images and events that are lined up exactly on each pixel, this will train your network exactly the same way as you would with a traditional kind of image-based network. So we found that this actually works very well. And one good thing that this allows us to do, actually, is it allows us to basically model any kind of noise in the event stream without having to explicitly do something about that. So for example, sometimes with the events, you might have a hot pixel which just continuously streams out noisy events for no reason. In this case, that would not be affected in the photometric loss, so the network will actually learn to ignore those kinds of things. However, one issue that we had with this loss function is that, well, you need good grayscale images for training. So for example, if you wanted to train a network that was in something like with fast motions or high dynamic range, you're kind of limited to either having to have kind of really slow motions or kind of bump up the lighting a lot. So in the work that we're presenting in CVPR this year, we have switched this out for kind of this focus loss idea, where we basically try to minimize an image of the average timestamp at each pixel. This is an idea that came from Cornelia's group at IROS last year. And it achieves a very similar thing where you basically get this kind of focused or deblurred image of the events. So if we look at an image of what this actually looks like, the idea here is that you want to basically estimate the motion in the image that will take all these points and then move them to a single point that they will originate from. And if you do that, hopefully you'll minimize the average timestamp in that image. So we've compared these methods against a kind of image-based unsupervised method called Unflow on our dataset, where we've collected ground truth optical flow by taking our ego motion and depth estimates and then applying a rigid motion model for each pixel. So if you have a relatively large motion, which kind of simulates high speed, then we found that this network actually does better on most of the sequences, at least. The intuition here is that if you have two frames and a large motion in between them, you really have no idea what actually happened in between, right? But with events, actually, you see every single pixel that every single point inside the stream has moved to. And so this gives the network much more information in order to kind of estimate this kind of flow or ego motion and depth or whatever you'd like. So some results from our optical flow network. We have a demo for this today as well. We found that basically once you train these networks for optical flow, they generalize to basically any kind of scene that you can throw at it. So for example here, we have some water flowing down this kind of small waterfall that we have. We have a ball that's thrown in front of the camera, and this is actually half of real time. And actually, if you look at the grayscale image, the ball doesn't really show up at all. It's moving through so quickly that you just see kind of this blurry streak inside the grayscale image. Finally, we have the sequence from our data set where we have a motorcycle that's basically riding at 140 kilometers an hour on the highway, and particularly at night. So even in these kind of really challenging scenes, these networks will generalize and give you very reasonable optical flow. So one last thing that we've done is kind of take a step beyond optical flow to kind of other types of motion estimates. So in this case, we decided to try to estimate the ego motion of the camera and the depth of every single point in the scene, kind of like the paper that I alluded to at the beginning. So if you have a network that will output a per pixel depth and then a camera ego motion, you can basically estimate the optical flow using kind of geometry, the relationship that we know between ego motion and flow. We can then take this optical flow and then apply exactly the same loss function that we had before. And now we have a network that will actually output ego motion and depth instead of optical flow, which is really nice. One other thing that we did is that if you do have stereo event cameras, which you do have in our data set, you can actually apply an additional loss that will allow your network to actually predict absolute scale. So instead of just knowing that, okay, my laptop is kind of further than this point on this podium, I actually know that, okay, my laptop is exactly 1 meter away. And this can be very powerful for a lot of applications. One issue that you have with this is that So we try to apply basically like a photometric loss between the blurred event images. But the problem is that two different event cameras might generate different number of events at each pixel. So if you're just trying to compare the kind of number of events at each pixel, they might not match up. So instead, we apply a census transform on the event images. And so it converts the image into basically, for each pixel, do I have more or less events than each of my neighbors? And so this makes it robust to basically the number of events generated at each pixel. So these are some of the results we had on our nighttime scene. So this is relatively challenging just because the noise properties also of these events, of these cameras, is different when you kind of get into these low light situations. So you can see that the depth estimates are very reasonable. We kind of trained on a driving sequence, but driving sequence in the daytime. One interesting thing is that because the camera does have such high temporal resolution, things like street lamps, which kind of flicker on and off at very high frequency, actually generate a lot of events that don't really fit these kind of models that we apply. And that's kind of why you see there's a slight bias in the ego motion estimates from the camera. So as kind of future work in this field, I think it's really important to actually figure out principled ways to either filter these out in the beginning, or just, if we're training networks or learning, ways to kind of learn to ignore these kinds of factors in us. So that's most of my talk. We have the code for at least our RSS submission online, and then we should have our CVPRW submission online shortly. And we have more citations here as well. Cool. Thanks.